طيب, so let's start now our meeting, and today we're going to discuss multiple topics. First, we'll talk about the trees, and then we'll talk about the recursion, how we can go through the recursion and get the complexity and analyzing the algorithm through the recursion and recursion tree. We're going to use the explanation, the back substitute, the method that depends on tree, and also the master theorem. So this is actually very straightforward. I think those who have already studied M180, they are aware of these details. Trees is one of the very basic and important data structure, which actually depends or relies on how to organize your data item, and it is very popular. I mean, it's used popularly in many applications, including your computer. Even when you create folders, subfolders, and files in your computer, you are using trees. Because, for example, when you open a folder called picture, and then you inside this folder you create another one folder, you call it, for example, 2019, and another folder called 2020, and you put some pictures inside them, you are creating trees of files and folders. So this is a very common application that is used in the area of computer science. Also in database, we have this application. In database, we have different tables which are related to each other in such organization. In programming, you have the inheritance. Inheritance, it's also tree, where you have the superclass and the subclasses and so on. In computer networks, we have networking topology, where we have the tree. It has a node and some the root, and it's some nodes connected to the root. So there are so many examples for trees in the area of computer science. So this is how we can create multiple folders and files within your computer in the form of trees. Let's go through some of the terminologies that are used in trees. First is the node. The node is the root. Sorry, the root is a node which has no parent. So this is the only node in the tree that has no parent. Node number A. So this is called the root. Now, internal the tree, we have so many nodes. So the nodes that are called internal nodes are those nodes which has at least one child. So this one has one child. So it's considered as internal node. This one has also two child. So it's considered as internal node. This one has three. So this is also internal node. A is also internal node because it has three, at least more than one child. But in case of E, I, J, K, G, H, D, all these nodes have no child. So we call them leaves. Yes, we call them leaf. And these are called external node. So it has two terms. Either we call it external nodes or we call it leaf. So they have no child. Now the ancestors of a node are the parent and grandparent and grand-grandparent and so on until you reach the root. So the ancestor of J is F, B, A. The ancestor of G is C, A. The ancestor of D is A. The ancestor of K is F, B, A, and so on. So here is the ancestor. Ancestor are the parent, the grandparent, and the grand-grandparent, and so on until you reach the. Okay, now the depth of the node. The depth is how many ancestors does the node have. So the depth of the node, for example, here J, how many ancestor, parent and grandparent it has? 1, 2, 3. So it has 3 parents and grandparents. So the depth is 3. So in order to find the depth of any node, you have to calculate how many ancestors does it have. Okay, Abdullah. Then depth of the node is measured by counting how many ancestors the node has. So this node, for example, G, it has 2 ancestors, C, A. K has 3 ancestors, 1, 2, 3, and so on. This is the depth of the node. Now, the height of the tree, this is a general term for the whole tree, and that is actually represent the maximum depth of the node. So, in order to find the height of the whole tree, this is not for specific node. This is for the tree in general. So, the height of the tree is actually the depth, the maximum depth of the node. So, you have to find the depth of each node. The maximum is the height. Yeah, in this case is the 3 because here is the maximum for these nodes I, j, and k, which is 3. Okay, the descendant of the node are the child and the grandchild and the grand-grandchild until you reach the leaf. So the descendant actually is the opposite of the ancestor. So here is, for example, the descendant of F is J. The descendant of P is F and J, and so on. So this is how we find the uh, the descendant of any node. The descendant is the number of child and grandchild that the node has. So, for example, here ya lama, for B, what is the descendant of B? We have to know how many child and grandchild does it have. So here we have 1, 2. So it has 1, 2. That is the maximum. No, 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 Sonia, no. طيب, like this, my voice is okay now. يا مشعل أو مشاعل, الاسم مش واضح. طيب, مشاعل. أوكي مشاعل, إحنا بنسأل الآن عن الدبث, عفوا الديسيدنت. الديسيدنت للنود هما التشايلد والجراند تشايلد. يعني هذا يعتبر ديسيدنت, هذا ديسيدنت للبي, هذا ديسيدنت للبي. أيضا هذول اللي هم الأحفاد اسمهم ديسيدنت أيضا للبي. فالديسيدنت هم الأولاد والأحفاد وأولاد الأحفاد وأحفاد الأحفاد إلى أن يصلوا للليفز اللي هم آخر نوع. هذول كلهم بنسميهم ديسيدنت. واضح يا مشاعل؟ تمام. طيب, siblings are actually the nodes which are the children of the same parents, اللي هم الأخوة لهم نفس الأب. Yeah, so I, J and K, they are from the same parent which is F. يعني هون ال I وال J وال K هم من نفس الأب, فبالتالي we call them siblings. ال E and F are siblings. Why? Because they are coming from B. G and H are siblings because they are coming from C, and so on. So siblings are nodes or children that are of the same, coming from the same parents. Okay. Also we have the subtrees. See, we can have the trees as a general, and the tree is composed of subtrees. So this is, for example, CGH is a subtree, BEF is a subtree, FIJK is a subtree. Even this BEFIJK, we can consider it as subtree, and so on. Yes, yes, yes. I didn't. Wait, wait. I'm coming to the bath now. Now the bath. Bath is actually the order of the nodes that are connected with each other. So for example, we have a path from A to F. What is the path from A to F? It is F, B, A. This is called the path. Okay, from K to A, it is K, F, B, A. Yes, it is a sequence of the nodes, not numbers. You have to give the sequence of the nodes itself. Yes, correct, Khulud. Yes, K, F, B, A. Yes, yes, as a path to show the path. In the path, actually, when you specify the list of nodes, it means what is the source and what is the destination. So for example, when you write here, let's write, okay, here we can have one example, BFK. So here, when you write BFK, means you are specifying the path from B to K. Clear? Okay, now we have a special type of trees that are part of the tree, which is the binary tree. The binary tree is a tree that has a maximum of two children. So it might have, the node might have two children, one child, or no child. If that is the case, then we call it binary tree. Of course, the previous example, we cannot consider it binary tree because this leaf F, it has three childs. So in this case, this is not a binary tree. So the binary tree, it's something like this. So yes, two or less, two or less, not only two. You see, for example, here B, it has two. This is one, this is one. In this case, E, it has two, but D has zero. So it is applicable, still applicable. Yeah, maximum of two, not two, maximum of two. So this is called binary tree. Binary tree. Now for the abstract data type trees, the abstract data type trees, because inside the trees, when you implement a tree, actually each node is designed to store specific data. So here, for example, you might store 5. So the tree is integer tree. Someone else might store strings, so it will be string tree. So that's why we call it tree abstract data type. So it's for generic data types. So here we have generic methods. These are the general methods that you can find in the abstract data type, which is the length of the tree is empty. This is a Boolean function which return true if there are no elements in the tree. Iterator positions, it return an object from the type iterator for looping. Yes. And we have also the iter. And also the access method, we have the root, parent, children, and number of children. These are for positions. Here for iterate, iter for iteration, position for returning the position. Yes. And we have some methods for queries, like is leaf, this is a question. You are sending an element, a node, to this function is leaf. If the node, sorry, has no child, then they call it leaf. So the boolean will be true. Same thing for the root. It will check if the node has parent or no. If it has no parent, it's root. Update method, it's called replace. You give it two element and it will replace O by B. Here is the abstract tree ADT tree in Python. You can go through the code. No, Lama. Yes, O by B. Yes. Time. Now we reach to the traversal. Now, tree traversal is actually the order of visiting the nodes, and each node must be visited one time only. For example, I have now three cities: Riyadh, Jeddah, Dammam. Let's consider that Riyadh is the capital, because capital. So let's consider it as a root. And Jeddah and Dammam are child of Riyadh. So I have now three nodes. Riyadh is the central, it's a root, and we have Jeddah, Dammam. Now, one of you might say, I want to visit this tree as follows: Riyadh, Jeddah, Dammam. Okay, this is one way. Somebody might say, no, I want to say Jeddah, Riyadh, Dammam. One else might say, no, I want to say Dammam, Jeddah, Riyadh. This is actually what we mean by tree traversal. Which order you want to follow in order to visit the nodes? All the nodes, but each node must be visited one time only. Now we have three ways to access and visit all the nodes in the trees. These are called pre-order, in-order, and post-order. And it is actually related to the location of the root in the order. So when we say pre-order, means you must visit the root first, then right, then left. Means right of the tree, left of the tree. Let me draw it for you. See, we have A, B, C. Now, if I said I am following the pre-order mechanism or traversal, then I must visit the root first, which is A, and then go to the left, I will visit B, and then to the right, which is C. But this is for the pre-order. So pre-order means it's all about where the root is located in the order. So pre means the root first. Type. Let's go to the post. So pre-order is done. Let's go to the post. Post means the root is at the end. So we start from left, B, then right, C, then root, A. So A, the root is posted. This is till the end of the order. So we have B, C, A. When we say in order, means the root is in the middle of the visit. So we start from left, which is B, then we visit the root A, and then we visit the right, which is C. Now the traverse of root is in the middle of the order. Yes, Abdullah. Yes, pre-order is ABC. So if you have a clear view about the orders and the procedure, it's very easy for you to go through any traversal process. See, for example, here we want to go the in order. Here, yeah, no, this is binary. Binary, it has two. See, before you start here answering such question, I would recommend you doing the following. Before you start the traverse, make a circle on the roots. So you have 3 roots. Okay, yes, we have one root here, but this is actually a root for E and D, and this one C is a root for F and G. Yes, so let's put mark on them, because every time you want to traverse, these are the nodes that must be specified according to the traversal method. Now start with the in order. If it is in order, you have to start from the left, root, right, right? Left, root, right. This is the in order. Left, root, right. So left, where is the most left? Go to the left, left, so it's D. D, let me change the color. So D, this is left. See, left, D, then root, B, and then E. Left, root, right. Okay, finish. I finished the whole left of the main tree. Then root, A. Now the A is in the middle. Then right. Now I go to the right of the tree. But from the right of the tree, you have to go to the left, root, right. So left, which is the F, right, C, G. What do you mean by the LVR, Abdul Hakim? انت بتقصد التيبل؟ Oh yes, okay, طب same thing. What is it different? طيب. Yes. Left, root, left, root, then right. This is for the in order. That's why, see, the root of the tree, the whole tree is A. So A is in the middle. See? Okay, this tree, B, the root of D and E. So it must be between B, D and E. See? D is between B and D. And C must be between F and G. That's correct. So C is between F and G. Now for the post order, we have to go from left, right, then root. Left, right, and then root. Left, right, root. So go to the left, D, most left. Then from D we go to E because it's a right. So left, right, then root B. So D, E, B. Good. Now we finish the left of the whole tree. Let's go to the right. Now we go to the right, not the root. The root is the end because this is a post order. Okay, from here we go to the left, which is F, most left. F, G, C. So we have the F, G, C. And then at the end we add the root of the whole tree, which is the A. So A is at the end of the visited list, and that is the post order. For the pre-order, the root is first. So A, then left, which is the B, and then we go to the D, and then E. Then we go to the right, starting from the root, which is C, then left F, then left right G. Here are more example. You can do this at home to traverse the trees and find the in-order, pre-order, and post-order traversal of the given tree. Which one? Which one, Lama? In this slide or the previous slide? Okay, where it is? Again, it go first from the root because this is a pre. So it will be root, right, left, right, root, left, right. So root is A. Then left. What is the left? This side is the left. And then from the left, we have the root. We start from the root and then go the left of the root and then the right of the root and that and so on. Okay. Okay. Now that is the subject that forced me to give this class, direct class, before I record it for you. It is about recursion. Recursion is one way of writing codes for solving problems, and it is basically relies on the idea or the concept of dividing the problem into smaller segments or smaller subproblems. Because once you divide the problem into smaller problem, it will become easier for you to solve. Sometimes if I give you complete equation and I write you to find the solution for that equation, you might not be able to find the solution. But if you divided that equation into smaller part, okay, or sub equations, then it might be much easier for you to solve it. So recursion depends on this concept. It depends on breaking the problem into smaller one and try to find a recursive solution where you have to call, the method is calling itself for solving the problem backward, solving the problem backward. So it is, if I want to illustrate the size of the problem, it starts like this. This is the size of the original problem. The idea of recursive is to break it into smaller size and one small segment, and then break this one big into smaller, and then again break it into smaller segment, see, and until you reach this point. And then when you reach to this point, this is the last point. Now it's very easy for you to solve this problem because it's very tiny, very small size problem. So once you solve it, you go backward because now you have the solution of this part, right? So now this is the only one missing. Now once you finish this, you go backward. Now you already have the solution of this big part, and so on. So the solution will be backward. And sometimes you might find actually difficulties in writing code for solving a problem without recursion. So what do you mean by, why do you need the recursive functions? Here we need the recursive function for analyzing the complexity of the algorithm. I will go through the examples, and that is actually the first one. When you have this method, if n is greater than 1, return a n minus 1, else return 1. So this method will continue running as long as the value of n is greater than 1. Once the value of n is not greater than 1, which means that it is equal 1 or less than 1, what will happen? The function will stop and return 1. ممتاز. Now if I give you this function and I ask you to find the complexity of this function, how we will be able to do so? Yeah, okay, I know it's n. Yeah, it's written here. It's written, but how it's n? Now that is the, I will let me here. I will stop now the slide and share with you another screen. Wait, yes. Okay, can you see now the white screen? Okay, so let's. Okay, can you see now the white screen? Okay, so let's start. Now, in the first round, this is the equation. I will write the equation again, which is the T n equal T n. Okay, I think I need to switch to the application. Wait. It's much better to go to PowerPoint. Now I think you can see the PowerPoint, right? Okay. Okay, we start now with the T. This is the original one. Tn equal Tn minus 1 plus C. This is the original one. Now in the first round, we will have this equation. In the second round, it will be Tn minus 1, which equal Tn minus 2 plus C. So what we have here is just minus 1, because every time in the recursion we minus 1 from the operation. We go backward, because we go backward. So every time you have to minus 1 to go backward, starting from n and then go backward. N minus 1, n minus 2, n minus 3, and so on. Yes. Yes, of course. You minus 1 from n. So wherever you see n, you minus from it 1. So here we have n. We minus 1 become n minus 1. And here we have n minus 1. It will become n minus 2. طيب, in the third round, let's minus another one. So it will be Tn minus 2 equal Tn minus 3 plus C. This is the third round. Now go to the fourth round. In the fourth round, we will have Tn minus 3 equal Tn minus 4 plus C. So in general, after 4 rounds, we will say that Tn equal Tn minus 4 plus C plus C plus C plus C. So it is Tn here, Tn here. This is the original Tn. Tn equal Tn minus 1. So Tn minus 1 equal Tn minus 2. I didn't remove anything. No, wait. It's a backward operation. Backward operation. See, I reached this point, right? Tn minus 3 equal Tn minus 4 plus C. Is it clear up to this point? Let's please focus before you start giving questions. Wait. So up to this point, we say that Tn minus 3, we can make more rounds. You can say Tn minus 4 equal Tn minus 5 plus C, and so on. But let's stop at this point. So Tn minus 3 equal Tn minus 4 plus C. Okay. Now, if you back to the original equation, it says Tn equal Tn minus 1 plus C. So Tn minus 1 here equal what? Based on this, equal Tn minus 2 plus C plus C, صح? So you can say that Tn equal Tn, هاي الأوريجينال Tn minus 1 زائد C, صح? This is the original one. Here, I just copy the same. Now replace N1 by its value here. So it will have the same thing. Tn minus 2 plus C plus C. Continue doing the same. You will reach to this point where Tn equal Tn minus 4 plus C plus C plus C plus C. 4 C's. You got it now? No, no, no. It's 4C. Yes. I didn't say C to the power 4. No. Because these are constant. Just you calculate C plus C plus C plus C. This is what we have done here, as you can see. Yes, exactly. Right. Now, until here, since it's clear, let's sum it up. We can say that Tn equal Tn minus 4 plus 5 C's, صح? Or sorry, 4 C's. 4 C's. So we have 4 C's, which is here. Yes. So Tn minus 4 plus 4 C's. This is actually only for 4 rounds. I will go to this slide to continue here. So I will write it again. So in the fourth round, I get this equation. Tn equal Tn minus 4 plus 4C. Now, if you continue, you will reach to the kth round, number k. Because you cannot continue forever, we can say that we have to repeat this process k times. So Tn at this time will equal Tn minus k, because we are replacing now the numbers here by k, plus kc. Yes, plus kc. So when should we stop? When should we stop? يعني احنا we cannot go forever. At some place we should stop. We will stop the rounds when n minus k equal 1. N minus k equal 1. Then we stop the equation. Why? Because when n minus k equal 1, then we reach the t of 1. And if you reach the t of 1, you have to stop, because that is the end. So n minus k equal 1, which means what I care about is the k. So k equal n minus 1. So this is the value of k. Yes, k equal n minus 1. Now I managed to find the value of k. What should we do? Now we substitute all the values of k by n minus 1. Wherever you see k, you have to substitute it by k to the power n. So I will write it again. So I will write it again. So the equation is, sorry. So the equation is T n equal T n minus k. Sorry. minus k, Tn minus k plus kc. This is the original one. So wherever there is k, replace it by n minus 1. So equal T n minus n minus 1. Here is minus plus n minus 1 c. So here we have T n minus 1 plus 1 plus n minus 1 c, which is equal to Tn plus T1 here, T1 plus n. And this function, as we said, we take the biggest n. Here we have n, so O of n. So the complexity of this function is O of n. Yes, sorry, yes. It's here, n minus n. Yes, you are right. Sorry. Yes. That's why it will be at the end 1 here. Yes. Unfortunately, yes, Abdullah. This is actually how we can raise the complexity. Yes, because we have here Tn, T of 1 is 1, and we have only n, so the complexity is n. That's it. We don't care about c. C is just constant. C is constant. Type. Here also you have other examples. I will back again to the I'll stop sharing this and go back. To where we stopped. So this is actually one example. You can go through it, and here is another one. See, I just want to highlight something here. I just want to show you why we got 1. Why we stopped when t of 1. When we reach t of 1, so we will have the value, this condition will be valid, which is if n is greater than 1. So if the value is t1, so it will return 1. That's why we stop. That's why t of 1 is 1. Here is another example. Now instead of c, we have n. Please go through it, through this example also by yourself. Do the same procedure I did just now. That's why I'll make it recorded, so you can at least go back to my example again and trace the code here. By the way, here in this formula, it depends, finding the series, the output here, it depends on arithmetic, the sum of arithmetic series, which is here. And you must memorize it. This one, you must memorize this formula. Here is another example. And I'm going actually to present another one, which is very important. Yes. Let me now introduce you another way, which is actually the trees. See this tree. How we can find or use the recursion tree method for analyzing the recursive algorithm. Now, if I ask you the previous way, the one I described just now is called the back substitute. Now this is called recursion tree. This is called recursion tree. So it depends on how you represent your trees for analyzing the algorithm. Now I have this method here, Tn equal 2Tn at 2 divided by 2 plus n. How we can use the recursion tree in order to find the complexity of this algorithm. Now let's start by doing this. Let me share the screen again. Yes, yes, n is the root. Now let me share the PowerPoint is clear now. Okay, good. So how to solve such problems? Start by writing again the function, which is Tn equal 2Tn divided by 2 plus n. Now we need to draw the recursive tree. So Tn is drawn as follows. See, this n here, this n is connected or added up to Tn divided by 2 repeated 2 times. So I have Tn divided by 2 plus n and another Tn divided by 2 plus n. So I can say that n here is the root. And this root is added up to two functions, Tn divided by 2 and Tn divided by 2. Why I repeat it 2 times? Because here I have the number 2. So it is repeated 2 times. Now, every time in the tree you have to divide it by 2. Every time you have to divide by 2. So this Tn divided by 2, if I divide it again into 2, it will be Tn divided by 4. It's Tn divided by 4. And this one is the same thing. Yes, Tn by 4 and Tn by 4. You have to continue doing this until the T is vanished. When the T is vanished يعني خلاص ندمر الشجرة. When the T is vanished, we continue until somehow we reach the point T of 1. So the leaf of the tree is all T of 1. Yes. We don't care whether the value is 0 or 1, but we reach T of 1. So it might be 0, T of 1 might be 0 or might be 1. But we reach T of 1. Here were the stopping condition. Okay. So how much load or how much work we have there. See, the total amount of work that is done at each level, we have different levels. Here we have done n times, and this level is repeated n times. No, yeah, sir, we don't care. We reach to 1 and number from T2 to 4 or 6. No, you might continue dividing n divided by 4 and then n divided by 8, because every time you might divide the number by 2. So n divided by 8, then 16, then 32, and so on. So we will come up with different levels, different levels. So here the first level, it needs a work of n times, and this level n times, and this level 3 n times, and you continue until the end. This one also require n times, n times. Until here is clear. I just divided it into trees, and from the trees I find how much time or how much load I need to work on every single level. طيب, how many n's now I have? Now in this diagram I have here 1n, 2n, 3n, but you don't know how many n's you have. No, this is not for n. See the dots here. I have so many dots. You cannot see it. Means I did not continue. I just finished when I divided into 4 by 4. Okay, yes, but no, we can represent the number of n's by equation. See, in the first level, level 0, we have n here in level 0, we have n divided by nothing, by 1, صح? So 2 to the power 0. Plus the second level, yes, 2 to the power 1. So n divided by 2 to the power 1 minus, sorry, not plus, not minus, is just counting the levels. Then what I have after that, n to the power, n divided by 2 to the power 2. And I will continue until I reach to the point where n is divided by 2 to the power k. 2 to the power k. See, every time in round 0, in level 1, I have 0. In level 2, I have 1. In level 3, I have 2. So 2 to the power k. Yes. Yes. Okay, so when should we stop? When we are going to stop? We will stop when we reach this level, which is the T1. So when we reach to the point where n divided by 2 to the power k equal 1, we stop. When we reach to this level, then we stop. So the stopping condition is when n divided by 2 to the power k equal 1. So at this point, when we reach to this point, now we need to find what the value of k is. What the value of k is. So n equal 2 to the power k. يعني انت لما يكون عندك هون بس اضرب الجهتين, multiply the two sides by 2k. So you will have n equal 2k. To find the k, you have to find the log. Use the log because you need looking for the k. So take the log for the two sides. So log of 2n equal log 2 to the power k. So the log will go, the 2 with the 2 will go. So k equal log n. Log n. Okay, now we reach to this point. So k equal log n. But how many times we have to repeat the k times? K for each level. Now this is the k log n, the work needed for each level. How many levels do I have? I have n levels, right? I have n levels. So the total will be n log n. Is it clear? See, I do understand that it might be a little bit difficult for some of you, but this one require intensive practice. I have clarified one example from each type, and in your slides you have other examples. Please go through the examples by yourself and try to do the back substitute and the recursive tree. And if you still confused, I might also offer you some other examples, which will help you as well. Yeah, sure. Actually, that's why I purposely wanted to have this class live before I record it. طيب. So it is clear. Shall I move? Okay. Now the last thing is the Master Theorem. This is based on the divide and conquer algorithm. Here, actually, the purpose of this kind of theorem is to divide the problem into which is of size n into smaller problem of size n divided by b. So we are again, the target is to divide the problem of size n into sub problems, and each sub problem has the size nb. That is the target or the aim of this theorem. So let's say that the cost for each stage, because we have an algorithm, the algorithm is divided into sub parts or two parts. Now let's say that the cost for each part of the algorithm is divided into two stages. First is to divide the big problem into smaller problem. In the second stage, we have to solve the small problems and then combine them back again to find the big solution. How? This is the big problem. I will divide it into smaller problem. Okay. This is the first stage. In the second stage, solve these problems. And then combine them back to form the big problem. So you have a problem of size n, divided into smaller one, solve them, then combine the solution. You will have the big solution. So the the role of the master theorem is exactly what is the time needed for the algorithm to solve the problem. What is the time needed for by the algorithm to solve the problem? And that is actually based on this simple equation. So this is the diagram just now I draw. We have two sub-problems, find solution, combine. So you have to memorize this theorem. Okay, you have to memorize it, because if you memorize it, you can solve any problem. It's very straightforward, very simple. See, we have the function Tn equal Atn divided by b. This is the smaller problem. Okay, so Tn divided by b, because we said we have the big problem n, you divided it into a set of problems, sub-problems, nb, 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 and so on. So this is the sub-problem. Okay, what is Fn? Fn is the time needed to divide the problem and combine the solution. We call it Fn. This is a function. So Fn is the function which represent the time needed for dividing the problem and combining the solution. Okay, what is the master theorem? Master theorem said you have here A, it's very important to know this, A and B, A and B. And also you have to know that for the function Fn, it must be within the range of O n to the power d. The big O notation of Fn must be within the O n to the power d. So d is the power of n here. Now the theorem said, check this condition. If A here is less than b to the power d, then you can say that the big O notation of this function is n to the power d. If not, check the other condition. Check A, does it equal to b to the power d? If yes, then the O notation of this function is n to the power d log n. That's why I said you have to memorize. If A is greater than b to the power d, then the big O notation is n to the power log b of A, or log A of b. Let's take this example. What is the big O notation of this function? Given that Tn has the big O notation On as a result. Wait. See, now A, what is the value of A? Here is the A. Here is the A. So A equal 1. B is the divided number, 2. So B equal 2. D is here, the N. N here is power of what? The N here is power of what? Of 1, صح? So D equal 1. So, يلا try to first condition. Is A less than B to the power D? Yeah, A is 1. B to the power D. B is 2 to the power 1 equal 2. Sorry, less. Less, not equal. Less. Yes. So 1 less than 2. Is that correct? Yes. So this is the big O notation of this function, which is O n to the power d, which is 1, which equal n. So the complexity of this function is O of n. Again, you are giving this function here. So A is 2. This is the value of A. And B is 2. And D, what is the value of D here? Why? يعني I know it's written 0. How it's 0? أيوة 0, yes, it's the power. It is 1 to the power 0. Here, this one. Let me delete this. Again, this is the A, this is the B, and here is the power. 1 is the power of 0. Yes. No, it's 1, 1. 1 to the power of 0. We consider this part for extracting the value of D. So D is 0. Now, if you find the calculation, you will find that this condition is true. Because A is bigger than B to the power D. A is 2. B equal to the power 0, which is 1. So 2 is bigger than 1. Okay, what is the complexity? Complexity is as follows. Let me clear all this. Yalla, complexity is O of n log B. What is the value of B? Is 2. Will A 2. So log 2 for base 2 هذه بتروح كلها بضل ال n. So it is O of n. And here are more examples for you to go through for practice. I know it might be a little bit tough today, not like other classes, but again, you need to go through all these examples again, please. And I have no problem to discuss with you your findings if you have any issues that face you. And also, you can send me by email, and I will try to help you as much as we can. So, do you have any issues, any problem? Okay, you most welcome. And inshallah, I will see you on next week to discuss the next meeting, inshallah. Thank you so much for your attendance and have a good night.